Hi, Fairy Godmother.
Hello, Cinderella. Welcome to the Emergency Princess Agency. How can I help you today?
Well, happily ever after isn't so happily ever after when your husband's afraid of mice.
Oh, I'm sorry, Cinderella. How can I help?
Do you have any love potions on you by chance?
I think I might. Each love potion right here represents a different type of love that the drinker will feel for you later. The first type of bond is ionic bonding.
An ionic bond is formed by the attraction between a positive and negative ion. This type of bonding occurs when one or more electrons from the valence shell of an atom are transferred to the valence shell of another atom. In chemistry, the atom that loses the electron is called the cation, and the atom that gains the electron is called the anion. Ionic bonding occurs between metals and nonmetals, usually making the metal a cation and the nonmetal an anion.
So, when there's ionic bonding, my Prince Charming will give me all his electrons freely? How romantic! But how will I know how strong the ionic bond will be? I don't want another fling. I want to find a perfect Prince Charming who will give me all of his free electrons.
Using Coulomb's law, we can use the equation E equals kQq over R to measure the strength of the ionic bond. E is the energy stored in the bonds and is otherwise known as the lattice energy. K is a constant and equals 2.31 times 10 to the negative 19th joules per nanometer. R is the distance between the two atoms and is measured in nanometers, and Q is the charge on each of the two ions, which can be plus or minus 1.
Well, ionic bonding seems very one-sided. Is there a type of bonding that the electrons will be shared?
Actually, yes, Cinderella. The second and third love potions are both covalent bonds. The second love potion is polar covalent bonds. The third love potion is non-polar covalent bonds. And then there's another type of covalent bond called covalent bonds.
If electrons are shared evenly in a covalent bond, the electronegativity difference will be between 0 and 0.4. If the electrons are not shared evenly, then the electronegativity difference will be greater than 0.4, creating a polar covalent. So the bond between hydrogen and oxygen in a water molecule is a polar covalent bond because the difference is 1.24, whereas in H2 molecule, the difference is 0, so it's a nonpolar covalent bond.
So, in a non-polar covalent bond, my Prince Charming and I would love each other the same. But in a polar covalent bond, my Prince Charming would love me more than I love him, but I would still love him.
You would still love him. The electrons would still be shared. Now, the last type of bonding you need to know about is metallic bonding.
This type of bond is otherwise known as a sea of electrons because the way the metals are bonded is through a network of freely flowing electrons. In real life, this is why metals are such good conductors of electricity, because they allow the flow of electrons to easily pass through their valence shells. In addition, it gives metals certain properties, such as ductility and malleability, because the metallic bonds do not hold the protons of atoms firmly in place.
So, in metallic bonding, the electrons flow from one valence shell to another. So, it's more like free hippie love than anything.
I guess you have a tough decision to make, Cinderella. Which love will you choose?
I can see ups and downs to each type of bonding. In ionic bonding, the attraction is strong, but it would be a very one-sided relationship. One of the atoms does all the work, donating the electron or electrons, and the other, more electronegative atom, merely accepts the electron. In covalent bonding, the electrons are shared between two atoms, but in polar covalent bonds, the sharing is unequal. I think I would like nonpolar covalent bonding the best. Not that the freely moving electrons in love in metallic bonding is bad, but I just don't know what I'm looking for right now.
Well, here you are, Cinderella. I wish you all the luck in finding your new Prince Charming using your non-polar covalent bonds.
Thank you, Fairy Godmother.
Hello, Fairy Godmother. Hello, Pocahontas. Welcome to the EPA. How can I help you today?
I have a problem. The white man has brought smallpox to my people. How would me and John Smith be in together when he can only give me this deadly disease?
Well, in chemistry, there's a way to write love notes to show your bond and attraction to John Smith, where you don't even have to risk getting smallpox.
Will you teach me?
Of course I'll teach you, but we need to go somewhere else, inside. In chemistry, a way to represent how atoms have bonded to each other, just as you have bonded to John Smith, are called Lewis electron dot structures. I will teach you how to write these dot structures so that you may send love notes to John Smith without getting smallpox. When writing Lewis structures, there are 6 rules you must follow.
The first rule is to always look for symmetry in the molecule. The second rule is to find a central atom. Usually this will be the atom with the least electronegativity, however there are a few exceptions. You then put hydrogens on the outside of the molecule. You then write the correct number of electrons around each of the atoms. You can adjust the number of electrons for a charge structure, such as a polyatomic ion. And finally, you must watch for double and triple bonds because sometimes they exist and you won't realize until the end.
There are a few other special exceptions that you need to know about. In a covalent bond, when both of the valence electrons come from one of the atoms in the bond, it's called a coordinate covalent bond.
So it would look like this.
I drew the hypochlorite ion, or ClO2-, using the rules for drawing Lewis structures. I looked for symmetry by using Cl as the central atom, although this is an exception because it's the most electronegative atom. I placed 6 valence electrons around each oxygen atom and 7 valence electrons around the chlorine atom. Because this is a negative ion, I added an extra valence electron to the chlorine atom and then drew the coordinate covalent bonds. Coordinate covalent bonds occur when two nonmetals bond and both of the bonding electrons come from one of the atoms.
So can I assume that there's always 8 electrons around any atom?
Well, most time you can assume that there are going to be 8, as described by the octet rule. There are a few special exceptions you need to know about.
The first is that hydrogen, helium, and lithium only need 2 electrons to be stable. So, for example, H2 shares 2 electrons and is a stable molecule. The second rule is that beryllium needs 4 electrons to be stable. So BeCl2, beryllium has 4 electrons and is a stable molecule. Boron needs 6 electrons to be stable and is stable in the molecule Bf3. The fourth rule is that any atom above the third ring can have more than 8 valence electrons. In these two examples, phosphorus has 10 shared valence electrons with the 5 different fluorine atoms. In the second example, xenon has 8 shared valence electrons with the 4 different fluorine atoms, and it also has 2 non-bonding electron pairs, which make 12 total valence electrons.
How do I show my love for John Smith in different ways?
That's actually called a delocalized bond. When you have valence electrons and they can be put in different positions in a bond to form different types of molecules, you combined all of the different delocalized bonds to form a resonance structure.
A resonance structure represents all possible electron positions in a bond. For example, the nitrate ion is represented like this to show the changing position of the double bond as shown through the dotted line, which is the delocalized bond. Resonance structures are considered a snapshot or a still photo of all possible electron arrangements. Other than writing love notes to John Smith, which is very useful, in real life you can use the electron dot structures to determine molecular geometry and a hybridization of molecules. In addition, the placement of the electrons determines the chemical properties of a molecule, so when you write the dot structures, you can see how a molecule will react in the presence of other molecules.
Thank you so much for teaching me how to write love notes to my John Smith. I really don't want to get smallpox.
Jasmine, why are you at the EPA?
I'm just so distraught. I think Aladdin's gonna leave me. Can a street rat really become a sultan? What should I do?
Well, if you give me something of Aladdin's and something of yours, I can tell you the bond, length, and strength of your relationship. So do you have some hair from Aladdin?
Well, here is some of my hair, and here is some of Aladdin's hair. Now tell me the strength of our relationship.
Well, I'm currently analyzing the bond, length, and strength of your molecules interacting together. The bond order is really what the bond, length, and strength depends on.
Bond order? What's that?
Bond order is the number of electron pairs involved in a bond. So in Na2S, the bond order is 2. As bond order increases, bond strength increases, and bond length decreases.
Tell me, fairy godmother, how strong is the bond between myself and Aladdin?
Well, let me see. Wow. Your bond strength is incredible. It's stronger than N2's triple bond. It's stronger than Jafar's bond to evil.
Wow, really?
Yeah.
I have to go tell Aladdin I love him. This is great news.
And they all lived happily ever after. The end.